This is perhaps the world's silliest boost converter. This was inspired by one of my brilliant coworkers that sent me a picture of his version of this thing. It was a picture of a variable capacitor with a 9-volt battery and a neon light and a bunch of springs, and it sort of planted a bug in my brain, and this is my version. The capacitor is from an old Hewlett-Packard distortion analyzer that unfortunately I had to get rid of, so I scavenged out the interesting bits and used the capacitor for this thing. So the way this thing works, or what it does, we'll get into the details shortly, is when the capacitance is maximum, I charge the capacitor to 9 volts with this little spring contact, and then as I reduce the capacitance, eventually the capacitor discharges across a neon light here. Typically, an instrument will have a gear train to make the knob more sensitive, a gear reduction, and I was able to swap out the gears here to make it flip back and forth nice and quickly. So a gear increase instead of a gear reduction. Okay, I guess we'll give away the punchline first. This is a neon glow lamp or a neon bulb connected to our world's silliest boost converter. So I'm going to hit the lights and actuate the converter. And if we look carefully, we should see a little orange flash. Okay, let's dive in. So why was that little flash of light such a big deal? Well, for those not familiar with neon lights, a neon light is, it's not incandescent, it doesn't have a filament. It's 2 electrodes enclosed in a little envelope with neon gas between them. And so the way these things work is they initially look like an open circuit, but once the voltage across the terminals exceeds a certain strike voltage, which can be quite high, 60, 70, 80 volts even, then the light starts to conduct. The glow is emitted, and after that, it basically conducts like a copper wire. It's like a short circuit with but with a fixed voltage across it. And we're going to dig into that a little deeper here. And this is our boost converter. So this is a pretty silly looking device here, and we're going to dig into its operation shortly. But just a couple more words about neon lights. I grew up playing with neon lights. This is my box of neon glow lamps here. Here's one that is mounted on a little straw, and the reason is you can scuff your feet across the floor and touch a doorknob and the light will flash. So static discharge will also light up a neon bulb quite nicely. Here is a slightly fancier one, a large bulb with sort of kind of looks like a hat with a split in the middle. So also a fun fact that a neon light has trouble starting in the dark with absolutely no light hitting the electrodes. There's nothing to sort of to get the current flow flowing. Let's see, what else? Oh, and books were written about neon lights. So here's an article from an old magazine, Novel Neon Lamp Oscillators, and somebody at some point wrote a book called Neon Lamps, Elements of Electronic Versatility. So here are 10s, 20s, 30s of pages on all different types of circuits that you can build with neon lights, logic circuits, oscillators, etc. And maybe I'll try to scan this to PDF at some point and hopefully not get into too much trouble. Okay, so let's dig in and explore the electrical behaviors of our neon light a little bit. So as usual, we're going to be taking measurements with our AD-ALM 2000, but neon lights are high voltage devices. We're going to be measuring voltages on the order of 60, 70, or 80 volts for the strike voltage of the bulb, and potentially hundreds for some of our test circuits here. The AD-ALM 2000 has 2 input ranges, a 2-volt input range and a 20-volt input range. So obviously that's not going to work directly, but it turns out we can take advantage of the front-end circuitry of the AD-ALM 2000 and build ourselves a little attenuator quite easily. So if we take a look at the reference manual for the M2K's internals, then there's actually a schematic of the analog front end. So here's a picture of the board. This is a detailed diagram of the internal circuitry. So we're going to go to the analog inputs, and what we notice here, if we go to the schematic, See, there's the A to D converter. Yeah, so here is the analog front end. We'll get this picture up on its own. So here is the input itself. And what I notice is I go first through an 820K resistor, then another 200K resistor, and then a 21K resistor. So 820K plus 200 is 1.2 megohms. Did I do that right? 1.02 megohms plus another 21K. So fundamentally, it's approximately a 1 megohm input impedance. So what if I just add a series resistor at the front end of my M2K here? And that's exactly what we've done. And so if we wanted to make an attenuation factor of 10, then we could put a 9 megohm resistor in series with the analog inputs, and that would actually work fine, except some of the measurements that we're taking are very high impedance. We're going to be measuring high voltages across very small capacitors, so the higher our input impedance, the better. So what we've done is taken 9 10 megohm resistors and a 9 megohm resistors for a total of 100 megohm input impedance and an attenuation factor of 100 to 1. And let's just draw that circuit out a little bit here. So here I've got a little loop of wire that's just a test input, and then I come into 1, 2, 3. We won't draw all of them. We'll draw some dots. 6, 7, 8, 9, and then finally these are all 10 meg. And our very last resistor is approximately 9 meg. And then we go into the M2K's input. So we've got 820K. And then let's see, what was that other value? 200K, 200K. And then finally, the last resistor is 21K. And we're actually going to be set in the low voltage range. So this is what the op-amp actually sees. And this is approximately an attenuation factor of 100. And I'm purposely being a little cavalier with my description because we're actually going to measure that attenuation factor. Our resistor tolerances add up, and rather than rely on the values, let's actually run some measurements. So the way we're going to do that is put a known fairly high voltage across our input divider and see what it registers on the M2K. The way I'm going to do that is with an old photo flash charger evaluation board. So let's get a meter over here and see what this thing is throwing out. Okay, so we'll get that in frame. And if I measure, this is the negative output, and the positive output, wow, look at that, 290 volts. So I don't want to put my tongue across those wires there. If I attenuate this by a factor of 100, I get 27 volts, which would kick my M2K into the high range, and I don't want to do that. Plus, the way this circuit works is it's hysteretic. The voltage will bleed down to some voltage, 270 or so, then it will boost back up to 300. This is intended as a keep-alive circuit for a digital camera of some sort. Okay, so how can we regulate this to a known medium-ish voltage? Well, why don't we use a neon light? So a neon light, we're going to find out, we're going to take some more measurements on this before too long, but a neon light can act as a crude voltage regulator. So what I'm going to do is connect a neon light, the neon light directly in across my output. And I should point out I've got a 1 megohm resistor soldered in series with this wire. So I'm limiting the current through my neon bulb. The reason I did that is so if I do get my fingers across this, I don't want to discharge this massive photo flash cap all at once. Okay, so what we're going to do is take that voltage and let's see how that registers. So if I measure, oops, let's get these in the other direction. Okay, 75 volts. Okay, so now I've got a crude 75 volt source that I can hook across my AD-ALM 2000 and see how that registers. So what I'm going to do is take advantage of my stacking banana jacks here. I'm going to connect that directly across my attenuator, and we'll make sure we get that back in frame. Okay, so look at this wonky setup. So I've got 300 volts regulated down to 75 volts. I've got 75 volts at the input to my attenuator here, and I'm measuring it with the AD-ALM 2000. So let's go over to Scopy and see what we've got. So if we look at Scopy, we've got a trace 1 sitting up here at about 700 millivolts or so. So remember, this is an attenuation factor of about 100. So this is, in reality, it's about 70 volts. So I can actually come over here and enter in 100 in my probe attenuation. Okay, and now you'll notice that the cursor is reading 70, 75, 80 volts here. So I've got a direct reading on the voltage. And so this is the DC value, but remember what we said earlier, that the maintained voltage of a neon light is less than the strike voltage, meaning it takes more voltage to get it to fire initially than it does to keep it lit. So how are we going to measure that maximum voltage? And the way we're going to do that, we'll move this out of the way, we're going to build a little relaxation oscillator out of this thing. So remember, this board over here is 300 volts. Okay, and I've got a 1 meg resistor, and then that goes into my neon bulb. Little dot to indicate neon gas. Okay, and so I've got a continuous current flowing through this neon bulb. So what we're going to do next is we're going to put a 6800 picofarad capacitor in parallel with the neon bulb. And what that's going to do, well, we'll see what that's going to do in a minute. So let's pop the capacitor in place. Okay, wow, look at that on Scopy here. So yeah, we can see this sort of in real time. And the reason that the frequency is varying is the photoflash capacitor is, remember, that's a hysteretic controller. So it's going to droop down to 250 and then back up to 300. That's going to cause the capacitor to charge faster and slower accordingly. So let's zoom in a little bit here, and we can just stop it. And let's take the cursor and see if we can get a read on what our maximum voltage here is. Okay, so delta V, so if I look here, 0.15 kilovolts. Wow, so this neon bulb, am I reading that right? Takes about 140 volts before it fires. So that's pretty high. And remember, at the beginning of the video, we are starting with 9 volts and we're firing this bulb. So that tells us that that boost converter gets up to at least 150 volts. All right, so how does this silly thing work? Well, just a quick review. This is a variable capacitor. It's actually got 4 sections, but I've got them all wired in parallel for maximum capacitance here. And just to review how this thing operates is I charge the capacitor to 9 volts at maximum capacitance, and then as I turn the knob, the capacitance drops, and then I finally contact the output terminal here and flash the light. So let's dig into the theory a little bit here. So let's draw our circuit. So I'm going to start out. I've got a parallel plate capacitor, and I'm drawing this as a capacitor that's sliding, even though these are sectors or semicircles that are rotating with respect to one another. Conceptually, it's the same. So I'm going to ground one side of the capacitor, and then on the other side, I'm going to draw a little switch that makes contact with my 9-volt battery when I'm at maximum capacitance. So we'll draw our battery here, and that's 9 volts. And then I have the ability to slide one plate of the capacitor, reducing the capacitance, and then finally I can make contact with another switch over here, and then discharge through my neon lights, a little dot for neon, and this side is grounded here. Okay, so I charge at one capacitance, and then let's draw with red pen, and then I discharge at this other capacitor at a lower capacitance, and then so the plate has moved effectively here. Okay, so what's going on? So some fundamental relationships here. A capacitor has a charge of the capacitance times the voltage. And I always like to keep in the back of my mind that 1 farad is 1 coulomb per volt. So if I have a 1 farad capacitor charged to 1 volt, then I have 1 coulomb of charge. Now, as I'm sliding this plate here, there's nothing to bleed off the charge. So the charge is conserved. And what that means is V2 is, let's see, V2 times C2 equals V1 times C1. So the charge is equal in both cases here. So to get at the second voltage, we're going to cancel out C2 over C2. These guys cancel. So I've got the second voltage is the initial voltage times the ratio of the capacitances by how much the capacitance dropped. Okay, and let's take a couple of measurements on this thing to see what sort of capacitances we're talking about and what sort of ratios we're talking about. So I've disconnected the battery, and let's get a capacitance meter over here. So we'll turn this guy on, and we'll set to the capacitance mode. We'll connect one lead to one side of the variable cap and the other to the other lead. And we'll make sure that that's visible. So I get about 74 picofarads at minimum capacitance. And then as I rotate the dial, I get about 2,172 picofarads. So that, and we'll do the math in a second here. So again, that is 74 picofarads. And then in the other position, it is 2171 picofarads. Okay, great. Okay, so that's a drop in capacitance of about a factor of 29.3, so almost 30x. So we can take a 9-volt battery, and then let's do the math real quick. 9 times 30 is, yeah, about 270 volts, so that's quite a boost factor here. Okay, so let's actually take some measurements and see if we can see that increase in voltage on the oscilloscope screen. So I've got banana jacks on the other side of this thing. We'll see if this is easier to see. And then we'll take our AD-ALM 2000 with our little high voltage probe here. And I'm going to put the clip on the fixed plate of the capacitor, and I'm going to connect ground. Let's see, we'll connect the, get this right? Yeah, so we've got the stator. Yeah, so this is the rotor, and that is going to connect to the ground side here. Okay, and then if we go over to Scopy here, you see I've got my 60 hertz noise that's sort of buzzing along here. Actually, we'll hit run. Okay, and then I'm going to, yeah, so we're going to hook the battery back up. And then let's see if we can see, yeah, so here's ground. Notice that the trace falls down to 0 volts, and then I'm going to go all the way to start charging it to 9 volts. There's that 9 volts. Okay, so now we're set up in normal mode, so we should be able to catch a few of these traces. Yeah, boy, look at that. See how we just barely see an increase in voltage? Why is that? Well, the reason is, remember I said earlier, we're using high-valued resistors, not so much for the attenuation factor, but so that I'm looking into a very high impedance. And the reason is my capacitances are pretty small. So 74 picofarads times 100 megohms is 74 milliseconds of time constant. And then same thing with, even at the highest capacitance, that's 217 milliseconds. And I'm moving this thing with my hand in human time. So literally, as soon as I start rotating, as soon as I break contact, yes, my voltage is increasing, but I'm also discharging through my measurement instrument here, through the probe. Okay, let's see if we can get a picture of this, of the spike at the very output here. So I'm not going to look at the voltage as the capacitor plates are being pulled apart. I'm going to look only at the output. Okay, and so now I am only going to, I should in theory only see the spike at the very end. So let's see if we can catch that. There it goes. Okay, let's move this up a little bit because we're not catching the whole waveform. Okay, and okay, so there's a lot going on here, and sure enough, I am measuring up at about 40 volts here. But again, the light flashed, so the reason I'm only at 40 volts is because I am bleeding off some charge, and I'm and you know, as soon as the probe contacts the output, it starts to discharge. And if we zoom in a little bit, let's try one more time. Yep. So the faster I go, the higher voltage I see, but it's still not that high. Again, that is a fault of my measurement instrument here. But, you know, just to show that we're not lying, let's hook up that neon light that takes 150 volts to fire and fire it off a few more times. Okay, so let's hit the lights and flash our light a few more times. Okay, so to wrap up, let's look at one more phenomenon here. So we did a little bit of math earlier where we basically started with conservation of charge, and we arrived at the fact that our second voltage is increased by a factor of the capacitance reduction. But what about the energy? So the energy in a capacitor is, or stored in a capacitor, is 1/2 C times the voltage squared, capacitance times the voltage squared. Okay, so let's see what happens when we plug in our situation here. So our second energy, E2, is equal to 1/2. Let's see, that's C2. Oh, sorry, that's actually C1. So our initial capacitance, let's see, times the C2 over C1, the factor that our capacitor has decreased by a factor of 30 in our case. And then let's see, that's going to be times the second voltage, which is C1 over C2 times voltage. And then this whole quantity is squared. Okay, so we can actually cancel out one of these guys. We can cancel out one of these squared terms, and what we end up with is E2 is 1/2 C1, our initial capacitance, times, we were left with one of these guys, C1 over C2 times voltage squared, our initial voltage squared. So what that says is that our energy went up by a factor of 30. How cool is that? We got something for nothing, didn't we? So how can that be? Well, it turns out that as we're sliding this capacitor, as we're moving the plates apart from one another, there's actually an electrostatic force between the plates. And that's actually what we're going to show in our next video here. I've already got proof of concept on this. We're going to take 2 copper plates, and we're going to put one of them on a kitchen scale and measure the force when we apply a high voltage between the two. But again, that's for the next video here. And yeah, so let's plug a couple of numbers in here. If we take our initial, capacitance is 2171 picofarads, so our energy 1 is 1/2 2171 pico times 9 squared. And that gives us 87 nanojoules. And then when we multiply that by 30, at the very end, we end up with 2.6 microjoules. Okay, so yes, our energy went up by a factor of 30, but it didn't come for free. That energy came from my hand, the force that it took my hand to turn those plates. And of course, there's a lot of friction in here that dominates, but there's a tiny force, a tiny torque on these plates here that I had to overcome in order to reduce that capacitance. Okay, we'll see you next time.